Resistive load refers to electrical components that consume power without introducing any reactive power. Examples of resistive loads include resistors and incandescent light bulbs. These loads create a purely resistive impedance in the circuit, causing the current and voltage to be in phase. Inductive load refers to electrical components that introduce inductance into the circuit. Examples of inductive loads include motors, transformers, and fluorescent lighting fixtures. These loads create a lagging power factor in the circuit, causing the current to lag behind the voltage. Contactors have a low maximum load rating for inductive loads compared to resistive loads. This is because inductive loads create a high inrush current when the contactor is initially closed, which can damage the contacts. Resistive loads have a higher maximum load rating for resistive loads because they do not create the same inrush current as inductive loads. Therefore, the maximum load capable of being carried by the contacts within the contactor is typically higher for resistive loads than inductive loads. Let's delve a little deeper into each of these concepts. Firstly, let's explore resistive loads in more detail. A purely resistive load is one where the voltage and current are in phase. This means that the power consumed by the load is simply the product of the voltage and the current. Resistive loads convert electrical energy into heat or light, as seen with resistors and incandescent light bulbs. These loads are relatively easy on switching devices like contactors, as the current flow is smooth and predictable. Secondly, we should examine inductive loads more closely. Inductive loads, on the other hand, store energy in a magnetic field. When a contactor closes to energize an inductive load, there is a surge of current known as inrush current. This inrush current can be several times higher than the steady-state current the load draws once it is running. The high inrush current puts significant stress on the contactor contacts, potentially causing them to overheat, pit, or even weld together over time. Examples of inductive loads include motors, which are found in countless applications from pumps and fans to compressors and machine tools, transformers, which are used to step up or step down voltage levels in power distribution systems, and fluorescent and LED lighting, which, while more efficient than incandescent bulbs, still present an inductive load due to the ballast or driver circuitry. Thirdly, we need to understand the impact of inrush current. The magnitude of the inrush current depends on several factors, including the size of the inductive load, the impedance of the power source, and the point on the voltage sine wave when the contactor closes. To mitigate the effects of inrush current, contactors used with inductive loads are often specifically designed to handle the higher current surge. These contactors may have heavier duty contacts, arc suppression features, or other design elements to improve their performance and longevity. The NEC or National Electrical Code provides guidelines for selecting contactors for different types of loads. It is important to consult the NEC and the manufacturer's specifications to ensure that the contactor is properly sized for the intended application. Sizing a contactor involves considering the load's voltage, current, and horsepower rating, as well as the duty cycle and ambient temperature. One important thing to note is the concept of horsepower. Many motors are rated in horsepower, and there are NEC tables that correlate horsepower to amperage for different voltage levels. For example, NEC table 430.250 provides the full load current for 3-phase alternating current motors. If you have a 5 horsepower 480 volt motor, you can use this table to find the corresponding full load current, which is approximately 7.6 amps. This value is crucial when selecting a contactor. The contactor's ampacity rating must be greater than or equal to the motor's full load current. Another important consideration is the service factor of the motor. The service factor is a multiplier that indicates how much overload the motor can handle for short periods. If the motor has a service factor greater than 1.0, you need to multiply the full load current by the service factor to determine the appropriate contactor size. Let's say the 5 horsepower motor has a service factor of 1.15. In this case, you would multiply 7.6 amps by 1.15, which gives you approximately 8.74 amps. The contactor you select should have an ampacity rating of at least 8.74 amps. Furthermore, you need to consider the interrupting rating of the contactor. The interrupting rating is the maximum short circuit current that the contactor can safely interrupt. This rating must be higher than the available fault current at the installation location. Calculating the available fault current requires a detailed analysis of the power system, including the transformer impedance, conductor size and length, and other factors. It is often necessary to consult with a qualified electrical engineer to determine the available fault current accurately. Let's look at an example scenario. Suppose you are installing a contactor to control a 10 horsepower 208 volt 3-phase motor with a service factor of 1.0. According to NEC table 430.250, the full load current for this motor is approximately 28 amps. Since the service factor is 1.0, you don't need to adjust the current value. Therefore, you would select a contactor with an ampacity rating of at least 28 amps. You would also need to ensure that the contactor's interrupting rating is sufficient for the available fault current at the installation location. Now let's consider a resistive load example. Imagine you are using a contactor to switch a bank of electric heaters with a total power consumption of 10 kilowatts at 240 volts. To determine the current, you would use the formula power equals voltage times current, or current equals power divided by voltage. In this case, the current is 10,000 watts divided by 240 volts, which equals approximately 41.7 amps. You would select a contactor with an ampacity rating of at least 41.7 amps. Since resistive loads do not have inrush current, the selection process is relatively straightforward. However, you still need to consider the interrupting rating and ensure that it is adequate for the available fault current. In addition to ampacity and interrupting rating, contactors also have a voltage rating. The voltage rating indicates the maximum voltage that the contactor can safely switch. It is crucial to select a contactor with a voltage rating that is equal to or greater than the system voltage. For example, if you are using a 480 volt system, you need to select a contactor with a voltage rating of at least 480 volts. Using a contactor with a lower voltage rating can be dangerous and may lead to equipment failure or even electrical shock. Another important factor to consider is the contactor's coil voltage. The coil voltage is the voltage required to energize the contactor coil and close the contacts. Contactors are available with various coil voltages such as 24 volts alternating current, 120 volts alternating current, 240 volts alternating current, and 480 volts alternating current. It is essential to select a contactor with a coil voltage that matches the available control voltage in your system. Using the wrong coil voltage can damage the contactor or prevent it from operating correctly. Furthermore, contactors are available in different pole configurations. The number of poles indicates the number of separate circuits that the contactor can switch. Common pole configurations include single pole, double pole, 3-pole, and 4-pole. The appropriate pole configuration depends on the application. For example, a 3-pole contactor is typically used to switch 3-phase power, while a single-pole contactor may be used to switch a single-phase circuit. In addition to these basic specifications, contactors may also have various auxiliary contacts. Auxiliary contacts are additional contacts that are mechanically linked to the main contact. These contacts can be used for various purposes, such as indicating the contactor's status, interlocking circuits, or providing signals to a control system. Auxiliary contacts are typically rated for lower currents than the main contacts, so it is important to check their specifications before using them. When selecting a contactor, it is also essential to consider the environmental conditions in which it will be operating. Contactors are available in different enclosure types such as open, enclosed, and explosion-proof. The appropriate enclosure type depends on the environment. For example, an open contactor is suitable for clean, dry environments, while an enclosed contactor is necessary for dusty or damp environments. An explosion-proof contactor is required for hazardous locations where flammable gases or vapors may be present. Proper installation and maintenance are crucial for ensuring the safe and reliable operation of contactors. Contactors should be installed by qualified electricians in accordance with the NEC and local electrical codes. Regular inspections should be performed to check for signs of wear, damage, or overheating. Loose connections should be tightened, and any damaged components should be replaced immediately. It is also important to keep the contactor clean and free from dust, dirt, and moisture. Dust and dirt can accumulate on the contacts and prevent them from making good electrical contact, while moisture can cause corrosion and lead to premature failure. In summary, selecting the right contactor for a specific application requires careful consideration of various factors, including the load type, voltage, current horsepower, service factor, interrupting rating, coil voltage, pole configuration, auxiliary contacts, and environmental conditions. Consulting the NEC, manufacturer's specifications, and qualified electrical professionals is essential to ensure that the contactor is properly sized, installed, and maintained for safe and reliable operation. Finally, let's review some best practices for working with contactors. Always de-energize the circuit before working on a contactor. Use appropriate personal protective equipment such as gloves and safety glasses. Follow the manufacturer's instructions for installation and maintenance. Inspect contactors regularly for signs of wear, damage, or overheating. Tighten loose connections and replace any damaged components promptly. Keep contactors clean and free from dust, dirt, and moisture. Never exceed the contactor's rated voltage or current. Use the correct coil voltage for the contactor. Select the appropriate enclosure type for the environment. Ensure that the contactor's interrupting rating is sufficient for the available fault current. By following these best practices, you can ensure the safe and reliable operation of contactors in your electrical systems. Now let's consider some specific types of contactors. Firstly, definite purpose contactors are designed for specific applications, such as HVAC systems, refrigeration equipment, and lighting control. These contactors are typically less expensive than general-purpose contactors, but they may not be suitable for all applications. Secondly, lighting contactors are designed specifically for switching lighting loads. These contactors often have features such as tungsten ratings and ballast ratings to handle the inrush current associated with lighting loads. Thirdly, motor starting contactors are designed for starting and stopping electric motors. These contactors typically have overload protection and other features to protect the motor from damage. In addition to these specific types of contactors, there are also various accessories available for contactors, such as overload relays, surge suppressors, and timers. Overload relays protect motors from overheating due to overloads or phase loss. Surge suppressors protect contactors from voltage transients and surges. Timers can be used to control the timing of contactor operations. When selecting contactor accessories, it is important to ensure that they are compatible with the contactor and the application. For example, overload relays should be sized appropriately for the motor's full load current, and surge suppressors should be rated for the system voltage. Remember that electrical work can be dangerous. It is important to have a thorough understanding of electrical safety practices and to follow all applicable codes and regulations. If you are not comfortable working with electricity, it is best to hire a qualified electrician. Safe work practices when working with electricity include the use of lockout-tagout procedures whenever you are working on equipment. This is in accordance with Occupational Safety and Health Administration OSHA standards. Proper use of PPE, or personal protective equipment, like safety glasses, insulated gloves, and appropriate clothing. Additionally, do not work on electrical equipment in damp or wet locations. Avoid wearing conductive jewelry like watches, rings, or necklaces. Always assume that electrical circuits are energized unless you have verified otherwise with appropriate testing equipment like a multimeter. The NEC provides a comprehensive set of rules and guidelines for electrical installations. Some important articles in the NEC related to contactors include Article 430, which covers motors, motor circuits, and motor controllers, Article 440, which covers air conditioning and refrigeration equipment, and Article 725, which covers Class 1, Class 2, and Class 3 remote control, signaling, and power limited circuits. These articles provide detailed requirements for the selection, installation, and protection of electrical equipment, including contactors. Familiarizing yourself with these articles is essential for ensuring compliance with the NEC. Furthermore, it is important to stay up to date with the latest revisions of the NEC, as the code is updated every 3 years to reflect changes in technology and industry best practices. Continuing education and training are crucial for electricians and other electrical professionals to maintain their knowledge and skills. Attending workshops, seminars, and online courses can help you stay informed about the latest developments in the electrical industry and improve your ability to perform your job safely and effectively. And lastly, always ensure proper grounding. Grounding provides a path for fault current to flow back to the source, which helps to trip circuit breakers or fuses and prevent electrical shock hazards. Grounding systems must be installed in accordance with the NEC and other applicable codes and standards. Common grounding methods include equipment grounding conductors, grounding electrodes, and bonding jumpers. By following these guidelines and practices, you can help to ensure the safety and reliability of electrical systems and equipment. Electrical work can be complex and challenging, but with the right knowledge, skills, and tools, you can perform your job safely and effectively.